97-year-old men who lift weights twice a week have measurably larger hippocampi than age-matched non-lifters. That sentence deserves a moment. The hippocampus is the brain's primary memory consolidation structure. It shrinks at a predictable rate as the human body ages. And for decades, the prescribed countermeasure was simple. Walk more. Get your steps in. 30 minutes a day. Keep moving. But researchers at the University of British Columbia, led by neuroscientist Teresa Liu Ambrose, published findings in 2010 that quietly dismantled that prescription. In a randomized controlled trial, women aged 65 to 75 who performed resistance training twice weekly showed a 13% increase in functional brain plasticity over 12 months. The walking group showed no such change. Pause. The walking group did not plateau. They did not show modest gains. They showed no measurable change in the neural architecture being studied. This is not a fringe result. It has been replicated, and it points to something that the mainstream conversation about exercise almost never addresses. Walking is not bad for you. Walking is genuinely beneficial in ways that are well documented and real. But when the question is, which form of movement most profoundly reshapes the biology of the human body at the cellular, hormonal, and neurological level, the data does not point to walking. It points to resistance. The question is why? And to answer that properly, we need to go much deeper than muscle. We need to go to the machinery itself. Here is the myth stated plainly. Walking is the safest, most accessible, and most effective form of exercise for the majority of humans. You have heard this from doctors, from public health campaigns, from wearable device companies whose entire product category is built on step counts. 10,000 steps became a cultural axiom, so thoroughly embedded that most people have never questioned where it originated. It originated in a 1960s Japanese marketing campaign for a pedometer called the Manpo-K. The name translates roughly to 10,000 step meter. There was no clinical trial behind that number. There was no physiology. There was a product name that became a health prescription for 60 years. Now, researchers at the Harvard T.H. Chan School of Public Health, led by Min Lee, published a 2019 study in JAMA Internal Medicine that did attempt to quantify the actual relationship between step count and mortality in older women. They found that benefits plateaued at approximately 7,500 steps per day. Beyond that threshold, additional steps produced no measurable reduction in mortality risk. The 10,000 step target had no physiological basis, and the actual ceiling of benefit was lower than the myth. But here is the deeper problem with the walking first narrative. It treats exercise as a single category of thing, when in fact different modes of physical stress trigger entirely different biological responses. Walking and resistance training are not on the same spectrum. They activate different molecular pathways, stimulate different hormonal cascades, and produce different long-term structural changes in tissue. Walking does not load bone to the threshold required to stimulate osteoblast activity at a clinically meaningful rate in adults over 50. Walking does not create sufficient mechanical tension on muscle protein to drive meaningful myofibrillar hypertrophy past the age of 40. Walking does not generate the acute hormonal environment that stimulates growth hormone and insulin-like growth factor, one secretion at levels associated with tissue remodeling. So the real question is not whether walking is good for you. It is. The question is, what biological machinery does walking fail to activate? And what does that absence cost the human body over time? The answer to that question requires a specific scientific framework. It comes from a field called mechanobiology, the study of how physical force is transduced into biochemical signals at the cellular level. Researchers at the Weiss Institute for Biologically Inspired Engineering at Harvard have spent years mapping the precise molecular cascade that begins the moment a muscle cell experiences mechanical load. The central figure in this cascade is a protein called mechanistic target of rapamycin, commonly called mTOR. It is not a hormone, it is a kinase, an enzyme that activates other proteins by adding phosphate groups to them. Think of mTOR as a master switch inside the cell. When it is on, the cell builds. When it is off, the cell either maintains or cannibalizes itself for fuel. Walking keeps mTOR largely inactive in skeletal muscle, The load is insufficient to cross the activation threshold in adults with typical muscle mass. Resistance training, specifically loading muscle to near failure, triggers mTOR activation through a pathway that begins at the cell membrane. To understand what that activation actually does, we need to go inside the cell, and we need a precise mechanical analogy to make sense of what we are looking at. Here is what nobody tells you. The sarcomere, the basic contractile unit of every muscle fibre, is not a simple rope being pulled. It is a ratchet, a molecular ratchet made of interlocking protein filaments called actin and myosin. Every time a myosin head binds to an actin filament and pivots, it pulls the actin in one direction and then detaches. Then it rebinds further along and pivots again. This is the cross-bridge cycle. It is the mechanism of muscular contraction at the nanometer scale. When you walk, these ratchets engage at low frequency and low force. Low, the myosin heads cycle through their binding and release at a rate matched to the modest energetic demand. The metabolic cost is covered almost entirely by oxidative phosphorylation in your mitochondria, using fat and glucose as fuel, delivering adenosine triphosphate at a steady, sustainable rate. When you perform a heavy resistance exercise, a squat near your 1 repetition maximum, a deadlift at 85% of your peak load, the demand on that ratchet system escalates dramatically. The nervous system recruits high-threshold motor units that have been dormant during all your walking. These units control the largest muscle fibers in the body, type 2X fibers, the ones with the highest force output and the lowest mitochondrial density. The actin-myosin ratchets in these fibers must operate at near maximum force. When the load exceeds what those ratchets can sustain without slipping, something critical happens. Microscopic disruptions form in the sarcomere structure, specifically at a region called the Z-disc, the anchor point of the actin filaments. These disruptions are not damage in the pathological sense, they are the signal. The Z-disc disruption triggers a mechanosensing cascade. Proteins called integrins, embedded in the cell membrane, detect the deformation and activate a signaling molecule called focal adhesion kinase. That kinase activates phosphoinositide 3 kinase, which activates protein kinase B, which activates mTOR. The entire chain from mechanical event to molecular signal takes milliseconds. mTOR, now activated, phosphorylates 2 downstream targets, S6 kinase 1 and eukaryotic initiation factor 4, epsilon binding protein. These 2 molecules are the translational machinery that actually reads messenger ribonucleic acid and assembles amino acids into new protein chains at the ribosome. What you have just witnessed, at the molecular level, is the manufacturing line being switched on. The sarcomere disruption is the foreman pulling the lever. The mTOR pathway is the electrical system that responds. And protein synthesis, specifically the construction of new actin and myosin proteins to repair and reinforce the disrupted sarcomere, is the actual product rolling off the line. Walking does not pull that lever. The load is insufficient to cause Z-disc disruption in healthy adult muscle at the intensities typical of recreational walking. The molecular manufacturing line stays idle. But the mTOR pathway is only the beginning. What happens over the following 24 to 72 hours after a resistance training session reveals a second biological cascade that walking does not touch at all. And this cascade may be the most consequential one for human health across a lifetime. When sarcomere disruption occurs at sufficient scale across multiple muscle groups, multiple sets, multiple repetitions, the immune system responds. Damaged muscle tissue releases signaling molecules called cytokines. Specifically, interleukin-6 is released from muscle cells themselves during and after heavy mechanical loading. This is unusual. Interleukin-6 is typically produced by immune cells in response to infection or injury. When skeletal muscle produces it in response to mechanical load, it functions as a myokine, a hormone secreted by muscle. This is the part most people never hear. Skeletal muscle is an endocrine organ. It secretes hormones. When you contract a large muscle mass under significant load, you are not just moving weight. You are triggering a hormonal secretion event that affects your brain, your liver, your adipose tissue, your pancreas, and your immune system simultaneously. Interleukin-6 released from muscle during resistance training travels through the bloodstream and reaches the liver, where it stimulates the production of insulin-like growth factor 1. That molecule crosses the blood-brain barrier. In the hippocampus, it stimulates neurogenesis, the formation of new neurons, primarily in a region called the dentate gyrus. This is the same structural change Teresa Liu Ambrose's team at the University of British Columbia was measuring in 2010. Walking generates a much smaller interleukin-6 response. The muscle mass engaged is lower. The mechanical load per fibre is lower. The total myokine output is lower. The downstream hormonal effect on the brain is correspondingly attenuated. But interleukin-6 is only one of more than 650 myokines that researchers have now identified as being secreted by skeletal muscle in response to contraction. The field of myokine research is young. The term itself was only coined in 2003 by Danish researcher Bente Klarlund Pedersen at the University of Copenhagen. Pedersen's team published the landmark paper establishing skeletal muscle as an endocrine organ in the journal Physiological Reviews. What that means in concrete terms is this. An average human body carries somewhere between 30 and 40% of its total mass as skeletal muscle. That is the largest organ system in the body by mass. For the entirety of modern medicine's history, that organ system was understood as a mechanical actuator. It moved bones, it generated force, it consumed fuel. The realization that it also secretes over 650 distinct signaling molecules, hormones that regulate metabolism, cognition, inflammation, immune function, and tissue repair across the entire body, is not a minor update to our understanding of exercise. It is a fundamental revision, and the critical variable that determines how much of that endocrine activity occurs is not duration. It is not frequency alone. It is mechanical load. The intensity of force applied to the muscle determines the magnitude of the myokine response. Low-load, long-duration activity, like walking, produces a qualitatively and quantitatively different hormonal environment than high-load resistance exercise. In a 2019 review published in Nature Reviews Endocrinology, researchers including Mark Fabrio at the Garvan Institute of Medical Research in Sydney documented this distinction with specificity. They noted that the anti-inflammatory myokine irisin, which stimulates the conversion of white adipose tissue to brown adipose tissue and has neuroprotective effects, is released preferentially in response to high-intensity mechanical loading rather than steady-state aerobic activity. An average person walking for 30 minutes generates roughly 150 to 200 kilocalories of energy expenditure and a modest transient myokine response. A person performing 45 minutes of compound resistance training, squats, deadlifts, rows, presses, generates a hormonal cascade that remains measurably elevated for up to 48 hours post-exercise. These are not the same biological event wearing the same label. Consider what that 48-hour hormonal window actually looks like in measurable terms. Researchers at the Karolinska Institute in Stockholm, led by Thomas Gustafsson, have used muscle biopsy data to trace the post-exercise molecular timeline with precision. In the first 2 hours after a resistance training session, messenger RNA transcripts for actin and myosin, the structural proteins of the sarcomere ratchet, increased by 3 to 5 times their resting concentrations. Ribosomal activity, measured by the rate of protein synthesis per unit of muscle tissue, peaks between 4 and 6 hours post-exercise. The mTOR pathway remains phosphorylated, meaning activated, for up to 24 hours in trained individuals who provide adequate amino acid availability. That 24-hour window of elevated protein synthesis is the manufacturing period. It is when the disrupted Z discs are repaired, not to their original state, but to a reinforced one. The sarcomere rebuilds thicker actin filaments. The density of myosin heads per unit volume increases slightly. Over weeks and months of consistent stimulus and recovery, those small incremental reinforcements compound into measurably larger, denser, stronger muscle fibers. This process has a name in the literature: myofibrillar hypertrophy. It is distinct from sarcoplasmic hypertrophy, the increase in the fluid and glycogen content of muscle cells that produces the pump's appearance shortly after training. Myofibrillar hypertrophy is structural. It is the actual reinforcement of the molecular machinery, and it is driven specifically by mTOR activation, which is driven specifically by Z-disc disruption, which is driven specifically by recruitment of high-threshold motor units under near-failure conditions. Walking does not initiate this sequence at any point in the chain. The question of how the resistance-trained body differs structurally from the aerobically adapted body leads directly to bone. This is where the argument against the walking-first prescription becomes most urgent and most personal for the approximately 200 million people worldwide diagnosed with osteoporosis or osteopenia. Bone is not static tissue. It is continuously remodeled by two competing cell types: osteoblasts, which build bone matrix, and osteoclasts, which resorb it. The balance between these two populations is regulated by mechanical loading through a process called Wolff's law, formalized by German anatomist Julius Wolff in 1892. Wolff's insight was that bone adapts its structure to the forces placed upon it. The cellular mechanism underlying Wolff's law was elucidated much later. Osteocytes, the most abundant bone cells, embedded within the bone matrix itself, are mechanosensors. When bone tissue deforms under load, fluid moves through tiny channels called lacunae canalicular networks surrounding the osteocytes. That fluid movement creates shear stress on the osteocyte membrane. The osteocyte then releases prostaglandins and nitric oxide, signaling molecules that stimulate osteoblast activity and suppress osteoclast activity. The threshold of mechanical strain required to trigger this osteocyte response is approximately 1,500 to 3,000 microstrain. Walking on flat ground generates approximately 300 to 500 microstrain in the tibia. Jogging generates approximately 1,200 microstrain. Heavy resistance exercise, specifically exercises like squats and deadlifts where compressive forces are transmitted through the axial skeleton, can generate between 2,000 and 4,000 microstrain. Walking's below the osteogenic threshold. In adults with already established bone density reduction, walking does not stimulate meaningful new bone formation. It is mechanically insufficient. This is not a matter of debate in the bone physiology literature. A 2022 meta-analysis published in the British Journal of Sports Medicine, examining 18 randomized controlled trials, found that resistance training produced significantly greater improvements in lumbar spine bone mineral density than aerobic exercise, including walking. The effect size was not marginal. For the lumbar spine, resistance training groups showed improvements of approximately 2 to 3% in bone mineral density over 12-month intervention periods, while walking groups showed no significant change from baseline. 2 to 3% sounds modest. But in the context of age-related bone loss, which proceeds at approximately 1% per year after age 40 and accelerates to 2 to 3% per year post-menopause in women, a 2 to 3% gain represents mechanically the recovery of 2 to 3 years of structural integrity. In a tissue that once lost cannot easily be rebuilt, that number matters enormously. The Liftmore trial also documented something rarely reported in coverage of the study. Participants, postmenopausal women with established osteoporosis, average age 65, reported no significant adverse events during the high-intensity training protocol. The assumption embedded in most clinical conservative guidance, that osteoporotic bone is too fragile to be loaded heavily, was not supported by the trial data. The bones were not too fragile for load, they were too fragile without it. This distinction is not semantic. It reverses the entire clinical logic that has kept millions of people with osteoporosis restricted to gentle walking programs that cannot, by the laws of bone mechanobiology, produce the osteogenic stimulus those bones need. Stuart Phillips at McMaster University made this point explicitly in a 2020 editorial in the British Journal of Sports Medicine. He argued that the precautionary principle in exercise medicine had been applied asymmetrically. The risks of vigorous exercise were weighed carefully against the assumed safety of sedentary or low-load behaviour, when in fact the evidence increasingly suggests that insufficient mechanical loading carries its own serious risk profile. The risk is not just weakening. The risk is the silent loss of the biological machinery that keeps bone, muscle, brain, and metabolic function integrated. Now here is where this stops being about bone density studies and starts being about you. The mechanical principle demonstrated by this evidence is not specific to aging populations or elite athletes. It is a fundamental property of the human body's adaptive systems. The body builds what it needs and dismantles what it does not. This principle, which exercise physiologists call the SAID principle, standing for specific adaptation to impose demands, operates at every level from the sarcomere to the skeleton to the synapse. The SAID principle was formalized in exercise science literature in the 1960s, though its conceptual roots go back to Wolff and further. What it states, in precise terms, is that biological tissue adapts specifically to the demands placed upon it. Not generally, not globally, specifically. And this is the next part the data actually shows. Walking imposes a specific demand: low force, rhythmic, cyclical movement. The body adapts specifically to that demand. It becomes more efficient at walking. Cardiovascular efficiency improves modestly. Capillary density in slow-twitch muscle fibers increases. Mitochondrial density in those fibers increases. These are real adaptations with real health value. But the body does not extrapolate. The osteogenic signal requires a load that walking does not deliver, so bone does not respond to walking beyond a certain baseline. The mTOR pathway requires Z-disc disruption that walking does not produce, so myofibrillar protein synthesis is not robustly stimulated by walking. The myokine cascade requires high-load muscle contraction that walking at recreational intensity does not achieve, so the endocrine output of skeletal muscle is attenuated. Researchers at McMaster University in Hamilton, led by Stuart Phillips, one of the most cited protein metabolism scientists in the world, have spent 2 decades mapping these distinctions with precision. Phillips and colleagues published a landmark 2016 paper in the American Journal of Clinical Nutrition, establishing that even very low loads, when taken to muscular failure, can stimulate maximal muscle protein synthesis. The critical variable is not the absolute weight on the bar. It is whether the muscle is recruited to near maximum effort. This finding resolved a long-standing debate and opened a critical door for older adults and individuals with joint limitations. You do not need to lift heavy weights to trigger the biological machinery of resistance adaptation. You need to lift any weight, even a light one, to the point where the last repetition is genuinely difficult to complete. The signal to the cell is not the number of kilograms. The signal is the recruitment of high-threshold motor units. Any load performed to near failure accomplishes that recruitment. This same SAID principle appears in contexts far beyond the weight room, and this next part is what the data actually shows. In competitive swimming, the force profiles of the pull phase in freestyle stroke have been analysed by researchers at the Norwegian School of Sport Sciences. Elite swimmers who incorporate dryland resistance training targeting the latissimus dorsi and posterior deltoid show superior water velocity per stroke cycle compared to swimmers of equivalent aerobic capacity who train exclusively in the pool. The mechanical specificity of adaptation means that swimming fitness, even at elite levels, does not fully transfer to the structural strength required for maximal propulsive force per stroke. In competitive cycling, a sport often held up as the gold standard of aerobic adaptation, researchers at the University of Copenhagen found that elite road cyclists who added periodized resistance training to their protocol over 16 weeks improved mean power output at lactate threshold by 7.2%, compared to a control group that maintained aerobic-only training volume. The mechanism was not cardiovascular, it was neuromuscular. Specifically, improved motor unit synchronization and increased firing rate of existing motor units, changes that resistance training produces and aerobic training alone does not. Parallel evidence comes from research in osteoporosis management. A 2018 study published in the Journal of Bone and Mineral Research, examining the LIFT-MORE trial conducted by Belinda Beck's team at Griffith University in Queensland, found that 2 sessions per week of supervised high-intensity resistance training improved bone mineral density at the femoral neck, the most fracture-vulnerable site in the aging skeleton, by an average of 2.9% in post-menopausal women with osteoporosis. The control group performing low-intensity exercise, including walking, showed no significant change. The mechanism is identical to what Phillips described for muscle. Recruitment matters more than absolute load. Proximity to failure matters. The biological signal is the firing of high-threshold motor units under conditions of progressive overload. So now when you feel the fatigue accumulating in the final repetitions of a set, that specific burning weight of effort just before you stop, you know what is actually happening inside your body at that moment. High threshold motor units that your nervous system has been conserving all day are being recruited for one of the few times those fibers will be asked to produce near maximum force. The Z discs in those sarcomeres are experiencing sufficient mechanical disruption to trigger the mTOR signaling cascade. The interleukin-6 is beginning to be released from those muscle cells into the bloodstream. The osteocytes in the bones absorbing compressive load are detecting fluid shear across their membranes and preparing to signal osteoblasts to begin building. All of that is happening simultaneously, in real time, because you continued past the moment when it felt easier to stop. And when the session is over and you feel that peculiar combination of exhaustion and satisfaction, the sensation that is often described as accomplishment, but is never adequately explained, you are detecting a hormonal environment that is genuinely unusual. Growth hormone has been released from the anterior pituitary at concentrations that dwarf what walking produces. Cortisol has spiked and will shortly normalize, priming the anabolic response window. Irisin is circulating. Interleukin-6 has cleared from the blood and triggered the downstream liver response. The cascade is running. The body is not simply recovering from the session, it is upgrading. Every system that was loaded beyond its comfortable operating range is now receiving a biochemical instruction to rebuild at a higher specification. The muscle is synthesizing new structural proteins. The bone that absorbed compressive force is receiving osteogenic signals. The brain is receiving the myokine-driven neurotrophin signal that the hippocampus uses to support the formation of new neural connections. This is not motivation language. This is the actual molecular sequence that occurs, documented in peer-reviewed literature, triggered specifically and reliably by the stimulus of near-failure resistance exercise. That does not happen after a walk, not at that scale, not at that magnitude.